So hello everyone, thank you very much for joining us today for this IRENA seminar. Today I am very excited to present David Hendriks. David has just completed his PhD. In fact, recently did his defense at the University of Surrey in the UK. Did excellently, and he is the resident expert in binary stellar evolution, all things binaries, mass transfer, and many other types of processes that he studies theoretically. He is also an expert in developing stellar population synthesis tools, which we'll hear a little bit more about today. And another aspect of his expertise is pair-instability supernovae. So David will be talking to us today about pulsational pair-instability supernovae in gravitational wave and electromagnetic transients. So David, if you'd like to put your slides up and take over.
Yeah. Let's see. All right. We can all see my slides, yes?
Yes, we can.
Hi, so I'm David. Thanks for the introduction. I'm David Hendriks from the University of Surrey. I'm going to give a talk about my recent paper, which was on pulsational pair-instability supernovae in electromagnetic and gravitational wave transients. And I'm going to try to solve the mystery of certain features in the primary mass distribution of black holes. So I've done this work together with Lieke van Son, Mathieu Renzo, my supervisor Rob Izzard, my former colleague Rob Farmer, and yours truly Rob Yates. And right, so the main driving thing about this research was the increase of gravitational wave mergers. Now, ever since 2015, we've been observing gravitational wave mergers, and most of them are binary black hole mergers. And specifically in the O3 phase and currently in the O4 phase, the numbers are really shooting up. From this collection of observations, we can now really start building some distribution of masses or spins or mass ratios. And now in this talk, I specifically will talk about the primary mass distribution, which basically means that I'm going to look at the most massive of the two black holes in a black hole binary. And what we see here in this slide is the second big data release and the third big data release and the posterior of the primary mass distribution based on the observations. And in both these distributions, we see that there's a certain feature. Well, there's several features. There's a strong peak here, which is kind of expected. But there's a second important feature here, which is a peak at 35 solar mass. And I'm going to try to reproduce this bump. And I'm going to specifically look at whether this bump can still be explained by pulsational pair-instability supernovae. We're talking about gravitational wave mergers, and I'm quickly going to say something about what type of gravitational waves we're talking about, what environment they're coming from, and what affects their outcome. I'm specifically talking about the in-spiral signal of gravitational waves. So there's a whole slew of types of gravitational waves, continuous ones, burst signals, stochastic backgrounds. I'm currently talking about the in-spiral of two black holes. And these black holes can have different environments that they're originating from. We need two compact objects that need to form somewhere, and there's a category of locations that they can form. The first, and I guess the most common, is the field, which is anywhere in the galaxy which is not particularly dense or surrounded by gas. The second is cluster dynamics of clusters, where other processes start playing a role, i.e. cluster dynamics. Or accretion disks, where these systems are surrounded by gas, are able to accrete a lot, which really affects their evolution further. of all these environments, the field is sort of the simplest. I guess we understand this isolated evolution quite well. But first, something to say about stellar evolution. A single star evolution is complex. I mean, stellar evolution is not a very simple process, but it is at least somewhat understood. And there are some properties that affect the evolution of stars more so than others. And I think the two most important ones are the mass of a star. If they're more massive, they evolve with a higher temperature, they're way more luminous, and that also means that they evolve a lot faster. And massive stars turn into supernovae and leave behind compact remnants or nothing. And the initial composition, which is usually called the metallicity. And with a higher metallicity, stars or the material has a higher opacity, so that affects the structure of stars. But that leads to more wind mass loss. So if you have a very metal poor environment, stars can remain more massive because they don't lose as much mass through winds. And that's going to be an important part here. Right, so that's about single stars. Right, and these are the two important parts for single stars. And now we're talking about binaries, right? If you have two black holes in the field that need to merge, then they need to be born together. So they are born together in isolation, which is sort of easy. There are no extra effects like dynamical interactions. And luckily, we understand the distributions of initial masses and periods relatively okay, at least locally. And we can then use our local knowledge to extrapolate this to earlier and different regions. But the fact that these stars are together basically opens up a whole extra set of possibilities for their evolution. Specifically, if stars evolve, they grow usually, and that can lead to mass transfer because there's something else nearby that pulls the mass away from them. So the material can be transferred from one star to another, sometimes in a stable fashion, sometimes in an unstable fashion. Other effects are tidal interactions. There's no mass being transferred between the stars at this point, but there is gravitational tidal interactions that can spin up the stars, can change the orbital periods, can change the eccentricities. And these stars can also merge. I mean, if they're close enough by each other and the mass transfer is unstable, sometimes their orbit doesn't contain enough energy to eject this envelope, and they merge. Now, importantly, if we want to have a binary black hole system, we cannot have the stars merge, and so the mass transfer interactions and the common envelope properties are quite an important aspect of the study that I'm going to talk about. And specifically, these binary stars can become black holes, binary black holes, but it's a rare thing. I don't talk about one binary system, right? I want to model a whole population of binary stars, and I want to do this fast because I want to look at the statistics. I want to vary certain physical aspects of our simulations, and in order to do this in a fast way, we use population synthesis, which is a method of rapidly evolving stars, usually through a set of approximations, either by using pre-calculated tables of stars or simplified stellar evolution analytic fits. Specifically, we cannot do detailed models of all the systems at every time step. That would take too long, because my aim is to evolve 16 million stars for each population, and I want to have at least 12 different populations to cover all the metallicities that are relevant. So to do this, we use a population synthesis code called binary-C, which is developed by my supervisor, Rob Izzard. And we're using the Python interface that I've developed for this to integrate everything nicely with other routines, other codes. so in this population synthesis code, there's a lot of knobs that we can tweak. Because things are not done self-consistently, we have scaling factors, we have switches to different prescriptions for the remnant masses, for the Roslob overflows, and these kind of things. And so those are all the blue blocks here. These are all different parameters. It's a schematic. There's many more knobs to turn. But the main point is here that we have initial distributions. As I said, we understand the distributions of masses or periods of stars, at least locally, relatively well. And we put all those stars through this evolution engine called binary-CEE. We calculate these stars, these systems, which more or less is, well, less than a second per system. So that's fast enough to do a whole bunch on a big computer. And then we look at the output distributions. And in our case, we look at binary black hole systems. And then between different simulations, we can make different assumptions about its supernova mechanism or other parts of the evolution here. Now, as I said, I want to evolve a whole bunch of different populations because we need to care about populations at different metallicities. So I evolve a set of 12 populations with metallicities between solar metallicity and very metal poor. And then I combine all the information that these populations gives us, the binary black holes with their properties and their rates. So the merger times are important and the rates are important. So we need to convert the mass turned into stars into the mass turned into merging black holes. And then we basically combine this with a star formation rate history. In this case, it's a cosmological star formation rate history because we're not looking at specific galaxies or origins. We take basically the whole universe. Specifically, we do not calculate population tree stars, but that would be a nice extension of our project. And then we calculate everything, and then we see what black holes merge. I'm going to make a small sidestep towards the supernova mechanism now, because I name dropped it a couple of times. But specifically, I'm interested in a certain type of supernova. It's called pulsational pair-instability supernovae, and how specifically this supernova type affects the distribution of black holes that we're going to see. There's a lot of steps going on in this slide, and I'm going to take my time a bit to explain this. So if we're in the situation of a very evolved star, and these have to be at least 38 solar masses or above, the inner structure and the temperature and density are such that well, the photons are energetic enough to produce electron-positron pairs. And that is a little bit of an issue for these stars because these are radiation pressure dominated. So if you remove photons from the core of the star, you remove this necessary pressure for the star to be structurally stable. What happens is that the star, the equation of state softens and the star becomes dynamically unstable. This leads to a collapse of the star. And this collapse is, if the collapse is not halted, the temperature increases so much so that the present nuclear fuel, in this case oxygen, is ignited. And that can lead to 3 different outcomes. Either in the most massive case, this explosion cannot halt this collapse. And the energy released in this explosion basically is used to photodisintegrate the material, and everything collapses into a black hole. But this only happens for the most massive black holes above 120 solar mass. The other case, when they're massive, they're massive but not so massive that they collapse entirely, is quite a disruptive fate. They explode entirely. The explosion is so strong that it basically leaves nothing behind. and basically all of the material will get returned to the interstellar medium. And the third scenario is the pulsational scenario, where the energy released in this explosion is enough to unbind some material, but not all of the material. And so you'll get this pulsating behavior where the star collapses, it sheds some material, and then cools down through neutrino cooling, and then sort of proceeds its normal evolution again, and then possibly undergoes the same instability yet another time, and this can happen a couple of times. And through this shedding of material, the star loses mass, and that sort of puts an upper cap on the black hole mass that we can get through stellar evolution, because either the star explodes entirely and leaves nothing behind, or it sheds material, and that basically caps the maximum black hole mass. Now, after it's done this a couple of times, it turns into a black hole through the normal core collapse mechanism, and well, that leads to a certain spectrum of black holes according to an initial core mass. Rob Farmer, who well, he did this study while I was doing my master thesis in Amsterdam. He calculated a whole range of core masses, calculated when they would become unstable, and calculated what pulsations and how much mass is removed from these pulsations. And in this case, he varies the metallicity in between the different colors and line styles. You see here that in this pulsation part, it basically leads to a turn-off. So instead of a continuous upwards line, this line of remnant mass black hole masses turns downward all the way up until 0, and then we have the pair instability where nothing is left behind. And this then essentially caps the maximum black hole mass. Now, that's quite interesting, and this then would probably lead to a certain peak in the gravitational wave primary mass distribution, and we're going to see whether the prediction of Rob Farmer here matches. And so in his paper, he provides a nice prescription so that we don't have to interpolate on all of these results. And the prescription more or less looks like the dash dotted line that we see here. So I've implemented this in my population synthesis code that I spoke about earlier. And if the dotted line here is the pre-supernova mass, so star evolves, loses material through winds, but the moment it undergoes supernova, just a moment before, it has this mass along the dotted line. And basically you see that everything below this, basically 38 solar mass, it turns into a black hole without losing extra mass. And from this point on, 38 upwards up until 60, the CO cores pulsate and lose mass. And from 60 CO core, it explodes entirely, right? Now, in the prescription implemented by Rob has a certain shape and a certain feature here. And this feature is a little bit of an artifact. So in a recent study in 2001, we basically took the results of that study from Rob Farmer, and we refitted it in a certain different way to make this a continuous line. And then we implement this into our population synthesis code to get the following distribution of binary black hole mergers. And there's a lot of things happening on this plot, so I'll explain each panel. So on the top plot, we see the merger rate. And the gray band that we see here is the merger rate observed / inferred by the LIGO observations. These are a modeling of the posterior likelihood of the observations, because we don't have this continuous distribution of observations just yet. And this is a function of the primary mass of the system. And then we see here in our orange our fiducial solution, which is the same, which originates from our implementation with this black line. Now, one striking thing that we immediately see here is that we do generate a peak, but it's not a peak at 35 solar mass. This is rather a peak at 45 to 50 solar mass. So there's something wrong here. There's a couple of other properties that I would like to highlight. Is that so this is the fraction of all these systems that underwent pulsational pair instability. So to confirm that this peak that we see here is indeed made up of systems that underwent this pulsational pair instability. So it's a good confirmation that whatever peak forms is formed through the pulsational pair instability supernovae. But also quite strikingly is that all of these systems at high masses, above 30 solar mass, basically all form with very highly eccentric, well, at birth, when both of these objects become black holes, they are highly eccentric. And that essentially is the reason that they will merge, because if they wouldn't have formed this eccentric, then the merging timescale would be way longer, and then we would probably see a different downward slope. This is something that I probably will do in a future paper, study the kick physics of supernovae. But I thought that was an interesting thing that we see here. So the companion, which is not as massive as the stars that we see here, plays a big role in allowing these systems to merge. And then the last thing is that from this 30 solar mass upwards, systems basically only merge through stable mass transfer or no mass transfer at all. So they don't undergo common envelope. And now, depending on how how into stellar physics you are, that's an interesting feat of this. But of this plot, the specific message here is that we find a peak, but it's at the wrong location. Now, in the next slide, I've taken away some of these channels, namely the common envelope channel, to see if the curve would fit overall better, and now it does. We see that the peak here is better reconstructed, but there's still some overdensities. And it wasn't the point of my paper was not to investigate the entire primary mass distribution, so we're basically letting this for a future study. But this can infer some interesting conclusions about common envelope physics, basically. In the paper of Rob Farmer, they did do a sensitivity study to certain effects, because as we saw in the implementation of Rob Farmer's results, the peak leads to the peak is at the wrong location. But are there any uncertainties that we can work with, or maybe motivate any changes to this? Now, a lot of the physical processes lead to very, very low uncertainty. With different neutrino physics, different mixing length timescales, different overshootings. They all lead to some variation in the most massive black hole location, but not that much. Except for this one here, the rates, that makes quite a big effect. But this was in 2019. So in my paper, I went to dig a little bit deeper into what processes could actually lead to a large change in the physics of pulsational pair instability, which might allow us to match the peak at the correct location. So I found a whole extra list of processes that could lead to some change in the pair instability peak location. Two very important one is the reaction rates. If the reaction rates change, then the structure of the core changes, and the amount of fuel that's present to fuel these pulsations also changes, and that has quite a big effect on the mapping from the CO core mass to black holes. But also things like rotation, additional mixing, additional cooling, additional heating, or axion pair instability have quite a big effect on the shape of this remnant mass distribution. Specifically, shifting downwards or upwards the CO core mass that undergoes this pair instability supernovae, and additional convection during the pair instability or structural changes that lead to differences in the core collapse could lead to extra mass loss from these stars. So basically there's two categories: either the range of CO cores that undergoes this pair-instability supernovae changes, or if a pair-instability supernova happens, there's additional mass loss. And I want to highlight two of these processes a little bit better. The one is the axion instability. So axions are, as of yet, a beyond standard model particles, but it doesn't stop people from speculating, like, what if they exist and what if they interact in some way with the standard model. Specifically, the existence of axions of a certain mass would affect the equation of state of stars, and it would affect the equation of state in a way that if these axions exist, stars of a different range would become unstable, very much like the pulsational pair instability instability. And so if there is an axion which has the same mass as an electron, it more or less affects the same region, but the region that becomes unstable grows a bit larger. And then we have axions of different masses. Higher masses leads to higher temperature when the instability occurs, and lower masses leads to a lower temperature regime, and also lower mass stars that undergo this pair instability or axion instability specifically. And what Sackstein and Juna-Krohn have calculated is that if there is an axion of the same mass of the electron, that would effectively lead to quite a significant downward shift of stars that undergo this instability. And so here on this dotted line, you see this is the standard model that basically I've been showing, and an axion of the electron mass would shift this curve downwards by about 10 solar mass to a lower peak location. And that's quite an interesting one, because previously we saw that 10 solar mass was basically the difference between the peak, what we find in the peak that the observations indicate. Going into the other direction, there's difference in reaction rates. This is a study by Eber and Van Ack, where they have improved and used different reaction rates for the carbon to oxygen fusion, and at the same time used a better temporal and spatial resolution, because if you have higher or lower rates, you need to properly resolve this. In this study, they find that using a different rate, one that at least at that time seemed to be more realistic, and properly resolving this leads to an upward shift of about 10 solar mass of the most massive black hole. And these different findings and all of these different reasons why there would be a shift in the black hole mass led us to take our toy model, put some extra parameters in here, and start shifting things left and right. So we can now move the range of stars that undergoes this instability by, say, 2 solar mass to lower, and then we see here this orange line, instead of this black line, now follows this curve, and we can basically shift that all the way down to maybe 10 solar mass or 15 solar mass downwards, or up, and we say, okay, pair instability only occurs for more massive stars, as indicated by improved reaction rates and a better resolved stellar models. So instead of having to calculate MESA models and follow the explosion, we basically now have two endpoints where we can shift in between, and that allows us to test, at least in this toy model way, if there's any way to resolve this mismatch of a peak. Additionally, we can also remove extra mass from these models, and we see this in the red dashed line. If we remove 5 solar mass, additionally on top of all of the normal pair instability, we see that this line shifts downwards. that has some subtle effects, which I will go and show now. So my idea now is we have this model which we have extra parameters in. Let's start to vary things to see if in either combination of these extra parameters, this shifting parameter or additional mass loss, can we match the peak. Now, if we take a series of additional mass losses, either 5 extra solar mass lost or 10 or 15 or 20, and again, fiducial is orange here, we are able to shift this peak a little bit downwards, which is about 10 solar mass, and a peak does form, but it doesn't reach the location of the actual peak that we observe. So we are able to move the peak somewhat with removing additional mass, and there are reasons why additional mass is expected, but we cannot recreate or match the peak in the correct location. If we start shifting the CO core mass range that undergoes pair instability, then we are able to match the observed location, but that requires us to remove or shift this range downward towards 15 solar mass. Whereas the newer rates indicate an increase of 10 solar mass, which basically places the peak location here. Now, that's very nice, and one might then ask, okay, well, cool, you now introduced 3 parameters in your model. Obviously, you can match things, which is true. And so we use additional observationals to sort of constrain or reject the models that we find here. So there's two models that we are highlighting here: the -15 solar mass downward shift, which more or less matches the peak location, and the +10, which is motivated by better resolved rates and better resolved stellar models. Okay, now we can compare this to something else. We can compare this to the transient rates, namely the supernova rates. And luckily we are observing many of them, and we can constrain this. So if we put the transient rates that I predict in this graph, and also the gravitational wave ones, we see for the pair instability, we see this orange line, and this is for our fiducial model. The green is the pulsational pair instability, and the blue is the core collapse supernova rate. And I've got a couple of observational rates, and the red rate that we see here matches very closely to the core collapse rate that we predict. So that's, I think, one nice sort of confirmation that we are at least in the same ballpark as the observations. The additional observational that I indicate here is the super-luminous supernova rate. And there are some, I'm going to make a remark on this, but let's now add the additional models that we have spoken about. So if I add the -15 solar mass CO core shift, which shifts it downwards to match the supernova, the gravitational wave peak, we see that these rates go up by more or less an order of magnitude, or a factor of at least 6. And if we shift it upwards, the CO core mass, then the rates go down, which is expected, because higher mass stars, there are less of them, and so the rate goes down. But if we now zoom in slightly in this region where we have observations, we see that the observations of the core collapse supernova match quite well. But we see that the pulsational pair instability always exceeds superluminous supernovae rates, and the pair instability rate exceeds the superluminous supernovae only for the -15 solar mass CO core shift, which is interesting, but the comparison isn't entirely fair, because not all of the pair instability supernovae are superluminous supernovae. So from detailed models and light curve modeling, we know that not all of these stars become superluminous supernovae. So we can play a little bit around with this, and Nickel and the rest of their team did this in 2013, and they basically concluded using detailed light curves that the rate of pulsational or the rate of pair instability supernovae cannot exceed 6 times 10 to the minus 6 that of the core collapse supernova rate. Now, if we draw a difference of 6 times 10 to the minus 6 ratio, then we end up in this blue line, and then we see that we are, while we're still overestimating, moving this CO core range downwards by 15 solar mass leads to a tension of a factor of at least 20 with what is allowed according to the study here. And so through this, we can basically rule out that the rate of pair instability supernovae that would lead from matching the gravitational wave signal would be in tension with the observed super-luminous supernova rate. So, as in essence, we have ruled out that pair instability or pulsational pair instability are the cause of this peak. Which is interesting because people have always thought that was the cause of the peak. And it has quite some implications on things like estimates of the fraction of field binary black holes versus cluster binary black holes, dark sirens, and a whole set of other implications. Moving the CO core mass upwards, matching this improved rate, relieves the tension slightly, but not entirely yet. So what I'm basically suggesting is that there is a peak in the gravitational wave signal at either 65 solar mass or slightly above this, which is not in tension with the superluminous supernova rate anymore, and is probably due to increased and improved rates of carbon to oxygen burning. And now that leaves us like, what causes the peak at 35 solar mass then? Now, there are other people that look at explaining this peak, and not necessarily through pair instability supernovae. One of them is Max Briel, and he looks at the combination of stable super Eddington mass transfer winds and chemically homogeneous evolving stars to explain the peak at 35 solar mass. And what he finds is that in this region of 35 solar mass, he clearly finds a peak. And he also clearly finds that basically in no significant way are pulsational pair instability contributing to this peak. These dashed lines are pulsational pair instability supernovae remnants. And you see that in this 35 solar mass region, basically only stable mass transfer leads to these systems. Other sources can be cluster dynamics, where dynamical interactions of black holes, and specifically the pairing of black holes, could lead to favor a region of 35 solar mass. Now, so this is by Fabio Antonini. Basically, what he finds is that systems or clusters can produce these black holes, but they need to be of at least 10 to the 4 solar mass per cubic kiloparsec, per cubic parsec, so that they are dense enough not to be kicked out of the cluster before merging, so that they need to merge in the system. And then they get peaks around this 35 solar mass location. And in the plot here on the right, we see some variations where they remove pulsational pair instability, and it removes the peak at 40 solar mass, but it still retains the peak at 30 solar mass. So somewhere in this region, they do form a peak, and it's slightly associated with pulsational pair instability, but not entirely. I think this study could, if they could zoom in this region, it would be quite interesting to see how they match things up there. Right, so this slide I didn't fill. So now a couple of preliminary things that I've been thinking of. So the rate of transients changes. Sorry. So the rate of transients changes, and becomes in tension with the observed rate. But also the rate or the yield of these supernova changes. So if the rate of these pulsational pair instability increases, then also the yield of these supernova, they return more mass to their environment because the IMF favors lower mass stars.
5 minutes, David.
Yeah. So if we look at these two scenarios, this is our model that fits the peak. We see that all right. Okay. So on the y-axis we have the fraction of the mass returned, the fraction of the star formation rate, basically. So if one solar mass forms into stars, then this fraction is returned through this supernova. And so I see these the y labels of this are removed, but this is more or less a 10 to the minus 2. This black line, which is the combination of both of these supernovae, and it basically shows that 1% of all material formed into stars is processed and returned to the interstellar medium through this supernova type, which doesn't sound like much, but generally not all mass is returned to the interstellar medium. It's about 10% of all the mass that's formed into stars will in general be returned. So suddenly this becomes quite a significant fraction of the total mass returned to the interstellar medium. And this could well become another source of tension with for example, galactic chemical evolution. So obviously in the upward shift, this is less so the case. Is at the 10 to the minus 3 scale. And so one of the things that I'm thinking of together with Rob Yates is to implement this into galactic chemical evolution codes, specifically the L galaxies code, where we provide yields for these supernova types, change them from left to right to see what fits best, but then also see whether these things become or are in tension with the yields that fit with the galactic abundances that we observe. And with our galaxies, we can readily do this, and we have done so recently in a paper that was released. Well, wasn't this last week or this week, Rob, where it got officially published?
Yeah, it was on arXiv a month ago and was finally published a couple of days ago.
Yeah. So we've built a pipeline to do this, and we can now easily add extra supernova types in this. And so these are future plans. Now, sort of a recap, we have implemented a newer prescription for the pair instability mass loss and the pulsational pair instability. We are not able to match it in our fiducial version, but we can make modifications to our version that leads to a match in the location. But then we create a tension with other observables, and this indicates that likely the 35 solar mass bump is not caused by pulsational pair instability supernova, and that it's likely a process of either cluster dynamics, binary interactions, or something more exotic. And I think I will leave it at this.